Hello. Let's talk now about some more molecular geometries and whether they're polar or nonpolar. And we've already looked at 2, 3, and 4 electron domains. And let's look at those involving 5. And so here's a molecule. And let's just say for grins that it's PCl5, phosphorus pentachloride. Its Lua structure might look something like this. And remember, the Lewis structure doesn't have to explicitly follow the electron domain geometry, but I've tried to do it in this instance. In that, when we're looking at electron domain geometry with 5 domains, this is a trigonal bipyramidal electron domain geometry, and it's also the molecular geometry or shape. And all the positions in this molecule are not equivalent in that these 3 atoms, they're 120 degrees from one another. They're trigonal planar. And they're at right angle to these other 2 chlorines, which are at an axial position. So if you think about the globe, the axis running from the North Pole to South Pole, the chlorine above and below are axial. The 3 chlorines around the equator are equatorial positions. So we got bond angles of 90 degrees and 120 degrees. And so these are the equatorial positions, and these 2 are the axial positions. In PCl5, the equatorials are all just alike. The axials are also just alike. So the equatorials cancel one another out, the axials cancel one another out. And so this molecule winds up being nonpolar. Now we could do a substitution reaction and maybe stick a hydrogen somewhere, be it either on an equatorial position or on an axial position. In which case, yes, the axials would cancel out, the equatorials would not. And so this molecule would wind up being a polar molecule. So what I've now drawn is PCl4H, we could call it. And that got a chlorine and a chlorine on an axial position with a hydrogen and those 2 chlorines. And so, yes, the axial positions cancel out, but everything is not equivalent around the equatorial positions. And so this molecule would have some polarity associated with it. Now, let's keep talking about this molecule or this molecular shape for a moment. And I could have 2 atoms that were different, in which case the axials still cancel one another out, but the equatorial positions do not, so it would be polar. If I substitute it in for that 3rd equatorial position, now all the equatorial positions are alike. They would cancel one another out. The axial positions would now cancel one another out. So even though everything's not totally equivalent, the axials are equivalent, the equatorials are equivalent, so this molecule winds up being nonpolar. Let me go back for just a second. And look at this one where we had 2 atoms that were different. They were both on the equator in equatorial positions. Just like their atoms are called isotopes there are atoms with the same number of protons that have different number of neutrons. Iso is a prefix meaning the same. There are things about molecules that are called isomers. They have the same atoms in them, but they're arranged differently. And so I could have had the two atoms that differ, both on the equatorial positions, in which case they don't cancel out that third one. I could have had one on the axial and one on the equatorial. And once again, the axials wouldn't cancel out, the equatorials wouldn't cancel out, so he's polar. But there's also another isomer that I could have, where the equatorials are just alike, and the axials also are just alike. And so in this instance, the axials cancel out and the equatorials cancel out. And so just something to be aware of. You got to look at the molecule as a whole as you're considering whether or not the molecule is polar or nonpolar. Now, remember we had this trigonal bipyramidal electron domain geometry. We have 5 domains around the central atom. One of them could be a non-bonding pair, in which case it comes off of an equatorial position, because that minimizes the repulsive forces by having a larger bond angle. And that gave us a seesaw molecular geometry. And so, once again, looking at this, axials cancel out, equatorials aren't all the same, so they don't cancel out. So that would be polar. We could have 2 non-bonding pairs of electrons. Once again, they would go on the equatorial position, and once again, this would be a polar molecule. If you remember, this was the T-shaped molecular geometry. And then the third way we could have a non-bonding pair of electrons on the central atom, you would also go on the equator in an equatorial position. So now all the equatorial positions are equivalent. They would cancel one another out. The axial positions cancel one another out. And so this molecule is nonpolar. This is a linear molecule, linear molecular geometry. And so that's some examples of polar or nonpolar with 5 electron domains from that trigonal bipyramidal electron domain geometry. So let's now look at an electron domain geometry of 6. This could be for something like sulfur hexafluoride. There's a Lewis structure, and all these bond angles are right angles. They're all 90 degrees. All the positions are equivalent. And since everything is equivalent, and all the atoms are the same, this molecule would wind up being nonpolar. Now we could do a substitution and replace one of those fluorines with a hydrogen. Now everything's not equivalent, and so this molecule would have some polarity associated with it. It would have a dipole moment. We could have 2 atoms that are substituted. If they're on adjacent atoms, the molecule winds up being polar. Even though there's some symmetry in the molecule, this, if you look at all those peripheral atoms as a sphere, that doesn't cancel out all of that part of the sphere. And so this molecule, where the 2 atoms are adjacent to one another in the octahedral electron geometry / molecular geometry, that winds up being polar. However, as we look back in the previous one, I sort of introduced this concept a little bit. so that we could see that most definitively in this example, where I've done a substitution. I got 4 atoms that are the same, 2 atoms that are of different type. These are opposite one another. And so now the 4 that are in this plane, they all cancel one another out. These 2 cancel one another out. So this molecule actually winds up being nonpolar. If you're trying to sort of visualize this, we don't talk about axial and equatorial. That's reserved for trigonal bipyramidal. But you could call this axial, and these 4 being equatorial. And so the 4 equatorial-like, they cancel one another. These 2 quote-unquote pseudo-axial are like, they cancel. So the molecule as a whole winds up being nonpolar. This molecule, I've now removed one of the atoms. This could be something like BRF5. We got bromine in the middle, in the center, 5 fluorines around here, and a non-bonding pair of electrons on that bromine. And so it's got octahedral electron geometry because there's 6 electron domains. But if you remember, we call that a square pyramid or square pyramidal. There you can see the square, and hopefully if I tilt it at that angle and you look at fill in these sides three-dimensionally, you got a 4-sided pyramid. There's that non-bonding pair of electrons down below. It does not cancel out that atom up above, and so this molecule would wind up being polar. And no matter whether we replace some of the atoms or not, made them different, those of course when I say it's non-polar, it's very much polar. It's a polar molecule. Same thing as if I change any of the atoms. So this very much is a polar molecule. Then the last example, something like xenon tetrafluoride. Where that other non-bonding pair of electrons is going to reside would be opposite the other non-bonding pair of electrons. So I've got 6 electron domains around that central atom. I got the 4 single bonds plus these non-bonding pairs. But when we talk about, so it's 6 octahedral electron domain geometry, we talk about the molecular geometry, we're only talking about the atoms that we can see, and that's square planar. And the atoms that are in this peripheral atoms in the square plane do cancel one another out, as do the non-bonding pair, and so that molecule winds up being nonpolar. But if I were to substitute for one of these atoms, so I've got 3 of one type and 1 of another, that molecule would wind up being polar because everything in this plane doesn't cancel. If I substitute 2 of them, it depends on where they're at. If they're on adjacent atoms, this side doesn't balance out that side, so it winds up being polar. Or if I have an isomer, this isomer where the 2 whites were together is what we sometimes refer to would be in the cis isomer. They're on the same side. Put them on the opposite side to where they're trans. It was called trans. The non-bonding pairs, once again, they cancel out. Now the 2 green atoms, whatever they might be, they would cancel out, and the 2 white ones would cancel out. So this one would wind up being nonpolar. Lots to think about. You got to look at the molecule as a whole and determine whether or not they're polar or nonpolar.